presentation.
Hi, everyone. I will be talking about the Scikit-Learn library in Python today. Can everyone hear me okay? Cool. So first off, my name is Joanna Kochaniak, and I usually go by Joe. I'm the co-founder and the CTO at GetUpside, which is a startup that's based in DC. And we provide cash back at local businesses and prove incremental profit to our merchants. And we are hiring, so if anyone's looking. And today what I'm going to talk about is I'm going to give a brief introduction to what machine learning is. Then I'll talk about how Scikit-Learn works and how GetUpside actually uses Scikit-Learn. So first off, has anyone here done any machine learning at work or at school? Cool, we have a few people. Has anyone used the Scikit-Learn library? Cool, also have a few people. Also, what is machine learning? This is a definition from Wikipedia, and it says that machine learning algorithms build a mathematical model based on sample data, known as training data, in order to make predictions or decisions without being explicitly programmed to perform the task. And there's many different types of machine learning, but the two types that Scikit-Learn can handle are supervised learning and unsupervised learning. With supervised learning, you have your training data, you have some inputs, samples, and each of those samples is mapped to an output. And you're training the computer to map a new input it's never seen before to one of these outputs. With unsupervised learning, you just have an input, you have data, it's not mapped to an output, and the computer is trying to discover some kind of patterns in those data. So for supervised learning, there's two different types of supervised learning. There's classification, and in this case, the output will be a class label. It's a discrete value. So for example, if you have an email message and you want to classify it as spam or not spam, that would be a classification problem. There's two choices. The other type of supervised learning is regression. And with regression, the output is a continuous variable, so it would be a number. For example, if you have a house, you know how many bedrooms it has, bathrooms, its location, you'd like to predict its price, which is a number, a continuous variable. With unsupervised learning, there's many different types of unsupervised. One example would be clustering. In this case, you have many different samples of data, and you're trying to find similar items in that data and create groups. So for example, if you have customers, and you want to find customers who are similar to one another and group them so that you can target marketing messages to each group. Anomaly detection is another type of unsupervised learning. And in this case, you're looking for patterns in the data and then finding data points that differ from the majority and are outliers in some way. So for example, fraud detection. If you've ever received a fraud alert on your phone from your bank saying, did you make this purchase? That is because they see that a purchase you made is unusual compared to your past purchases. And that would be an example of anomaly detection. So this is all kind of theoretical. I have a little example here to actually kind of visualize what it looks like. Let's see how this looks. So what I have here is I have some data that I've created. I've just created data points, x and y coordinates. And for each of these samples, so I have 15 examples, 15 points. For each of them, I've mapped them to a category. So this is an example of supervised learning, a classification problem. And you can see right here, my computer screen is going insane because of the screen sharing, but I have squares, circles, and triangles, and I've kind of manually grouped them where they appear to be in space. And what I did is I trained a Scikit-Learn classification algorithm on this data, and it's asking me right here, click any point to predict its category. So maybe if I click here, can anyone tell me what do you think it'll predict, which category? Square, cool, let's see. I think I clicked. There we go. Predicted category square. What if I click over here? Circle. Oh, it actually guessed triangle, interesting. Circle. So I think it thinks triangles are this entire spot over here, and over here in the middle, it's thinking circles are along this axis, which is still pretty reasonable. All right, let's close this. And here we have unsupervised data. So again, I have the same points. I have x and y coordinates that map right here to this graph, but I didn't assign them to categories. So in this case, we want to cluster this data in some way and assign categories based on those clusters. So it's asking me how many clusters. I'm going to try 5, because with this algorithm, it requires a number of clusters, and once it knows how many you want, it will group that data. So let's try 5. It grouped my data into 5 clusters. And it did put them by where they appear in space pretty closely, but it doesn't look quite right because we have 5 clusters, but it really looks more like 3, so let's try 3. And now we're back to pretty much our original graph. It automatically detected that these ones are similar, these are similar, and these are a third group. And visualize this in 3 dimensions. A computer can use math how computers are so powerful. Wow.
Your only input so far are coordinates?
Yes. Yep. So in those examples, I had 2 and 3-dimensional coordinates. All right, so machine learning, the most important thing with machine learning is to have some data, because you can't learn if you don't have data to learn on. So in Scikit-Learn, it comes with some built-in data sets. There's, for example, the iris data set, which is kind of a toy data set. There's only 150 examples in there. Then it comes with some real-world data sets that you can play with and learn how to use the algorithms. It also comes with utilities in the datasets modules for generating your own datasets. And if you have some data of your own that you want to run machine learning on, Pandas and NumPy, those libraries are very useful for loading, say, CSV data or whatever format you happen to have. Is there a lot of feedback, or am I just hearing it?
There's feedback.
Okay, I couldn't tell if it was like because I'm over here. Is there anything we could do about that? Okay, cool. So this is an example of the iris data set, which is part of Scikit-Learn. Can you still hear me? Okay, that's way better. All right, so in the iris data set, you have 4 features, and for each one of these rows is an example of a flower in iris, and you have the sepal length, the width, the petal length, and the petal width. And what it's the category is the type of iris that it is. And you can see here that it's 4-dimensional data, so you have 4 features for each of your flowers. And how that's represented in Scikit-Learn, if you actually loaded up that data set in Scikit-Learn, it uses the bunch library. If you're not familiar with it, a bunch object acts very much as a dict. It's a subclass of a dictionary, but it allows you to access the attributes, the keys, using the dot notation. So if you load up the iris dataset, what you'll see is dataset.data will contain the feature vectors. Dataset.featureNames contains the names for each of the features. And target contains the class, because this is a supervised learning. And the target names will tell you the name of that class. And I'll load that up live really quick just so we can see how it looks. So let's make this bigger so we're not getting craziness in the background. From sklearn, import datasets. And if I load up iris, I can see that I have 150 flowers, and each of them has 4 dimensions. If I look at it, I can see here's all the data, 150 of them. If I look at the feature names, this maps each of these indices to the name of the feature. So 5.9 right here is the sepal length of this last flower. And iris.target contains the category for each one of these samples. So they're just numbers, which then are mapped in target names. So this 2 right here says that this last flower is category 2. And if I do iris.target names, I will see what these numbers actually mean. So this 0 is a setosa, the 1 is versicolor, and the 2 is virginica. And you can see one more thing. So if I do iris.target.shape, you'll see that I have 150 targets. So I have a class map to each of these 150 flowers in my feature vectors. And while I'm in here, let me show you one more fun thing, which is this is the iris data set plotted from Scikit-Learn. And you can see there's 150 points, and there are the setosas, the versicolors, the virginicas. And because we can't visualize 4-dimensional space, I have the petal width is plotted as a color here. But you can kind of see that the setosas are forming a cluster down here, and then the triangles are up here. And you can kind of imagine how, using some math, you could figure out an algorithm to say, if I have a new random data point, which of these groups does it belong to? Okay, let's get back to this. And by the way, this plot that I just ran and the example I did earlier, those are available on my GitHub. And I have a link in the slides, which I can send out. Okay, so when we're machine learning, for supervised learning, there's the phase where we're training our model and it's learning something from the data. But once it's learned, you need to do something with that model. And generally, you're going to have real-world data that you plug into that model to see what it outputs. But before you put it out there in the real world, you'd like to have some idea of how well your model performs. So that's where the testing phase comes in. So generally, when you're working with machine learning, you're going to have a phase where you train on your data, and then you test. You do a final evaluation of that model and compare its performance on the labeled data you already have. And in order to do any learning, supervised learning, you always need to have data, and then you need the labels, which are the outputs, the categories for each of your samples. But if you wanted to train your model and then get an idea of how it performs on real data, if you test your model on the very same data that it trained on, there's a possibility that your model is overfitting, and it's learning the noise in that training data without actually being generalizable to real-world data. And you can't tell how overfitted it is if you're testing on that same data. So generally, what you'd like to do is the data that you have that's curated and labeled, you want to split that up into 2 sets. And you would have your training data, and this is the data you use to teach your model, and you hold out a separate set for test data. And you never train the model on that data. It doesn't see it till that final evaluation where you get an idea of its accuracy. And I won't get too deep into this, but there's also the concept of a validation set. So many of the machine learning models are kind of complex and require tuning of some parameters. And in order to tune those parameters, you need to do some cycle of testing to get an idea of the current performance. If you use your test set for that, then you're potentially learning the noise in that test set. And so it's good to have a third set, which is your validation set. And as you're training and tuning parameters, you're training on training data and then validating on the validation set and kind of doing cycles until you're happy with your model. And then you test again on that final set that it's never seen before. And with cross-validation, this is a very common technique. Again, I don't want to get deep into the details here, but I want you to be aware that this is, there are methods in Scikit-Learn for doing this. There's this cross-validation module. What you do with this technique is you split up your training data into multiple folds. And for example, usually you'd have 5 or 10 folds, and in this example here, I have 5 folds. And then you would train and test 5 different times. And each time you use one of the folds as your validation set, and you're training on the remaining data. So you're training on this data and then testing on data that you did not train on. But you do that 5 times, and you take the average across these 5 different training to get the performance for those parameters. And you're finding your parameters. Eventually, when you're finally happy with your model, that is when you test on the final test data that you've never seen before. Okay, so far, everything I've talked about has been numerical data. I had the coordinates, the iris data was numbers, but what can we do if our problem is not an actual, your data is not in numerical format, and we still want to run machine learning? Well, Scikit-Learn provides some utilities for that. There's a feature extraction module, and it has utilities for converting text and image data into numerical feature vectors. So an example problem would be document classification. So I think I mentioned this earlier. Imagine you have some text messages and you want to classify them either as ham, which means it's a valid text message, or spam, which is something you don't want to read. So this is a real data set that I downloaded from Kaggle.com here, and it has several thousand of these text messages which have been classified. How can I convert these to feature vectors that I can train on? As we said, Scikit-Learn requires numerical vectors, as we saw earlier, and all of them need to be the same length. Whenever we had that iris data, we saw that every flower had 4 features. And here we see that each of these text messages is a different length. And also, you can't do math on words. So how can we convert these words into numbers that we can do math on? So there's something called the bag of words model. This is very commonly used for text processing. The first thing we do is we tokenize the text. We split it up into the words. We consider each of those words to be a feature. And then we assign each of those features to an index to make our vectors. And for every document, we count the number of times that word occurred, and that is the value of that feature for that document. So let's look at an example. Here I have a toy example. I have 3 sentences. Each of these sentences is a document. And I import my Count Vectorizer from Scikit-Learn. And this is going to do the tokenizing for me. So I create an instance of the Count Vectorizer. Then I call fit transform. And anytime you see the word fit, that means that Scikit-Learn is learning something from data. So it's learning what are the features in this text variable that has 3 sentences. If I call get feature names on it, so it's done the tokenizing, it's extracted the features. The feature names that it's found is another, away, cat. As you can see, these are the words that occurred in these documents. And if I get the vectors that I created by calling my transform, it has now created 3 vectors. And so there's 1 vector for each of these sentences, and each vector has 7 different features. And this is how it actually looks. So I have 3 sentences. I have 7 features, which are the words occurring in these sentences. And for every sentence, I have the count of the number of times that word occurred in a sentence. So now I have some numerical vectors I can actually run machine learning on. So quick aside on why did I call this a bag of words? So the reason this model is called a bag of words is because it doesn't take into account the relative position of the words. So I have 2 sentences here, Fred likes Bob and Bob likes Fred. In English, we can tell that these are both different sentences with different meanings. But in the bag of words model, they end up with the same feature vector, just 1, 1, 1. And we've lost that information about which word occurred first. So this is called a bag of words because it's like we're breaking up our sentence into words. We're just throwing them in the bag, shaking them up, and we've lost information about the position of the words. Okay, back to our dogs and cats. So you might have noticed when we extracted these features here, 1 word, the word A, was not extracted. We have the dog chased a cat. But that was not extracted as a feature. So why is that? Well, when you create a Count Vectorizer in Scikit-Learn, you can choose to configure it in many ways. And one of the things you can set is the token pattern. And that's just a regular expression which determines how to separate the sentence into words. And by default, that token pattern will only extract words or tokens that are at least 2 characters long. So here, let's try, what if we created our own custom regular expression? Here, I'm just pulling out any alphanumerical string that's at least 1 character long. So again, I create my vectors from the same texts. And here are the vectors that were created using this regular expression here, where I overrode the default. And you can see that now we have the word A was extracted as a feature. Another important concept with vectorizers is min-df and max-df. So these are also parameters you can set on a vectorizer. Min-df stands for minimum document frequency, and what that means is only extract words which occur in a minimum of some number of documents. Max-df is the maximum document frequency, so that is only extract words that occur in at most this many documents. And for each of them, it's kind of interesting because you can actually set them, you have to set them to a number, but if you set them to an integer versus a float, it has slightly different behavior. So if you set the min or max df to an integer, that means an absolute number of documents. So if I set it to the min df to 5, that would mean only extract words that occur in at least 5 documents. If you set it to a float, it has to be between 0 and 1, and it's a proportion of documents. So if I set it to 0.5, that would mean only extract words that occur in at least 50% of documents. And the defaults for these if you don't specify these when you're creating your count vectorizer, min-df will default to 1, which is an integer. So that means only extract words that occur in at least one document, which effectively extracts all words. And max-df is set to 1.0, which means only extract words that occur in at most 100% of documents, which again will by default extract all words. Cool, so let's see how the min and max-df affects our text that we saw before. So originally, when we didn't set anything on our count vectorizer, these are the words we extracted. Now if we set min-df to 2, what words do we get? We see we dropped a couple words. So what this means is only extract words that occur in at least 2 documents. So we can see that, so for example, another and away were no longer extracted because they occur in only one document. If we set our max-df to 2, we get almost all the same words, but the word the was dropped because it occurs in all 3 documents, and we have a max-df of 2. Another concept that's interesting, I won't get into it too deep, but we've been using the count vectorizer, which by default sets the value of each of our features to the raw number of times that word occurred in the document. But you can set that number to many different things. You can scale it in different ways. And TF-IDF is a very frequently used format for processing documents. And what that is, it stands for term frequency times inverse document frequency. The term frequency is that raw number of occurrences, how many times this word occurred in a document. That's what the count vectorizer does. The inverse document frequency attempts to figure out how specific a word is and how much information provides about this document. So it's dividing the number of documents containing the word, the total number of documents divided by the number of documents containing the word. So the fewer documents that contain the word, the higher the IDF will be. So that allows you to scale and sort of pull out which are the interesting words versus something like the might occur many times in every document. And it might seem interesting, oh, it occurs so many times in this document, but then you realize, oh, it occurs in every document. It's not a very interesting word. So this is just a way of scaling to try to figure out which words are actually relevant. And Scikit-Learn, of course, provides some methods for doing TF-IDF automatically. There's a TF-IDF transformer, which can, if you already have vectors in another way, you can transform them to a TF-IDF, or you can use the TF-IDF vectorizer immediately and just do your TF-IDF off the bat. And of course, here's some links for that. Okay, let's get a little bit into the Scikit-Learn API. So there's a white paper here that I've linked which describes the API here, but they've tried to stick to the same API everywhere, so it's pretty easy to swap out and use different machine learning algorithms that they develop. And the estimator is one of the most interesting ones. So this is any object that is learning something from data. So that would always have a fit method. And we saw that before when we were fitting our vectorizer on our training data. And that when you call .fit on an object, it's always going to modify the object that you're calling it on. So after I call .fit with this data, this classifier is now, it's learned some internal model of what this data looked like. And then there's predictors. Predictors are things that predict an output for an input. So once I've trained my classifier, it now has that model inside of it, and I can call predict on some new data, and it will give me an output based on what it's learned. There's also transformers, and transformers are anything that transforms data from one format to another. So there's different types of pre-processing modules, things like that. And you might notice that some objects actually have a fit_transform method, and that's just a shortcut for calling fit and then calling transform. So earlier we were calling fit transform on our sentences, which was fitting to learn what are the features, the words within these sentences, and then transforming them into vectors. Okay, so let's get back to a cool real example and see if we can train a classifier. So we had that ham versus spam data set. Let's load it up, and I'm not doing the slide because I would probably forget and make a mistake, but all this code would actually work if you typed it in. So I'm using the pandas library here, and when I downloaded that data set, it was tab delimited. So here I'm saying delimiter tab, and it didn't have headers, so I'm telling it that the first column is the category, ham or spam, and the second column is the text message itself. So once I read it in, if I look at the shape of my ham span data set, I see that I have 5,500 data samples. And so that means I have 5,500 text messages. And there's 2 columns right now because the first column is category, then I have my message. Then I'm going to split it up into training and test data like we talked about earlier so that I can, after I train my model, I can evaluate its performance. And Scikit-Learn has train, test, split utility methods that allow me to do that automatically. So I call this train, test, split, and I'm giving it a test size of 0.3. What that means is I will hold out 30% of my data to be the test set, and then 70% will be the training. And it returns a tuple, so I get my training data, then my testing data, then I get the categories for my training data and the categories for my test data. So if I look at what it's done after it's split, it has determined 3,900 of those text messages to be training data, 1,600 to be the test data, so that's about 30% of our original 5,500. I have the categories for my training data, which map, again, 3,900. And then I have my test categories. So in order to do any machine learning, we need to convert that data into vectors. So I'm going to import my Count Vectorizer. I'm using all the defaults here just to see how it works. And I'm fitting again, so the vectorizer is learning about this data. And then I'm transforming, after I've learned, I'm transforming these text messages into vectors. And after I look at that, I see I have 3,900 text messages, so now I have 3,900 vectors. And each of those vectors has 7,200 dimensions, which means that I had 7,200 unique words in that data set.
You wrote the regex yourself for the token pattern?
No, so this actually is the default. When you create a count vectorizer, this is the default. You can see here it has W and then W plus, which would be 1 word character followed by at least 1 more, and that's why it was the 2 or more that we saw earlier.
So that's auto-generated?
This is the default one, yes. When you create your count vectorizer without specifying anything. Okay, so let's try to train a classifier. So I have my training data. I'm going to use Logistic Regression just to see how that works. So I create my classifier, and then I call .fit, which means it's learning, and I'm giving it the training data and then the outputs for each of those data. Now, if I want to test it, I need to convert my test messages. These are still just raw text. I need to convert those to the same exact format as my training data in order to be able to run my classifier on it. So here I'm calling the same vectorizer. This vectorizer, we fit it earlier and it learned the shape of the training data. We have to use that same one since it knows about the features in the training data. And if we called fit again with the test data, we would get completely different vectors, different words pulled out. So we have to reuse that same vectorizer instance that was trained on the training data, transform our test data into vectors, and then we can call classifier.score. So this is a nice little utility in Scikit-Learn, which is calling predict for each of the data samples in here, and then actually determining the accuracy, comparing it to the known category, and giving me a percentage. And we can see that our classifier, just using all the defaults, performed at 98.3% on predicting whether a text message is real or spam. And just for fun, let's use a different algorithm. So here I'm creating a multinomial naive Bayes classifier instead of the logistic regression. Again, we call .fit on our training data. And I'm not transforming my text messages again. I'm just reusing the vectors I created before. And I call score on the test vectors, and I see I got 98.6%. So just by swapping out basically one line, creating an instance of a different class, I've now improved my score already by using a different algorithm for machine learning. Cool, so we can train our models, but we actually probably want to run them in production on some real data. So how do I save my model so I can load it up at any time and run it? I don't want to retrain my model anytime I want to predict something. So you can use the Pickle Library, which is Python's library for serializing objects. And if you want to do that, you can write out to a string. So you take just your classifier object and you dump it, and then you can reload it from that same string. That works fine, but Scikit-Learn actually recommends using the joblib implementation, and that is because joblib is optimized for very large NumPy arrays and other objects that tend to occur in machine learning models. Works very similar to Pickle, There's dump and load methods. One of the differences is you can't dump to a string, but you can dump to a file. So here I'm going to dump my trained classifier to a file and then load it up again from that same file. And then I could call predict or score whatever I want on that classifier. However, we have to remember that anytime we're dealing with non-numerical data, if we're doing any kind of pre-processing on that data, if we use some type of object to transform that data, we'll want to save out that trained object as well, because our vectorizer was also fit. It's learned something about our text messages. So if I wanted to run my ham versus spam, I'd have to remember I actually need to serialize and save both the vectorizer and the classifier so that any new text messages I get, I can convert them using the same vectorizer into the right format that our classifier was trained on. So I could just dump a tuple of my vectorizer classifier out to a file and then load them both up and use them again. And here's just a few little tips when you're pickling. Of course, never unpickle untrusted data. Something that Scikit-Learn points out is if you serialize your model and you created it in one version of Scikit-Learn, always make sure that you load it up into that same version of Scikit-Learn. It's unsupported to load with a different version. It could work, but it could cause some problems that are hard to detect. Cool. So now I'll get into how does GetUpside actually use Scikit-Learn in the real world. So first off, I think I mentioned a little bit at the beginning, we're an app that provides cash back. You open the app, you see a map of businesses around you, you can claim an offer, then you upload a photo of your receipt from your purchase, and you get cash back. If you download the app, use my referral code. It'll give you some extra money, give me some extra money. All right, so how does this app work? Well, it's hard to transcribe receipts. Obviously, text recognition is not an easy problem. Receipts are particularly difficult because they're often, sometimes the printer is out of paper, only half the receipt is there, that type of thing. But what we try to do is we run OCR, so optical character recognition, to extract the text from the receipt. Then we extract fields from that text, so things like how many gallons you bought, how much you paid for it. And for fields that we couldn't extract automatically from our OCR, we use Amazon Mechanical Turk, which is basically a crowdsourcing platform where you can put questions up and people all around the world will answer them. So we just put up a photo of the receipt and say, how many gallons were bought in this receipt? Someone does that. If for some reason the Mechanical Turkers weren't able to extract that information, we have a final step of review where we have an internal tool that our operators use to look at the receipts and extract those last few things that we couldn't do automatically. So Mechanical Turk is pretty expensive. We pay 1 penny for every receipt that someone looks at, and then having in-house operators is expensive. So obviously we want to automate as much as we possibly can. And for some fields, there's additional validations we can use that help us to figure out some fields. For example, we always know that how much you paid will be equal to the gas price times how many gallons you bought. And so that helps us know if we extracted the right thing. But one problem that's not super easy is to tell if the receipt is actually from the right station. So you could claim an offer at BP, go across the street to Exxon, then upload a picture of your Exxon receipt. But we can't give you money for that because the offer was from BP. And receipts aren't super great. Like here I have 4 examples of receipts, and I put the address we have in the database on file for that receipt. You can see some of them match pretty clearly. But for example, over here, I have Martin Luther King Jr. Highway in the database, but on the receipt, it prints as MLK Ave. For these 2 receipts, there's no address printed anywhere on here, so it's kind of hard to know where the receipt is from. So can we apply machine learning to this problem to help us tell what site a given receipt came from? So again, let's see, we OCR every receipt, we convert it to text. We can say that every receipt is a document, and the station it's from is the category. That sounds like a supervised learning problem, very similar to the ham versus spam we just did. So we would convert each one of those receipt documents to a feature vector, and then we would train our machine learning model on those documents and the station categories, the outputs, to see if it can learn, if it receives a new receipt, which station is it from. So let's go ahead and do that. So first we OCR each receipt. So here's an example receipt, and here is the text that our OCR system extracted for it. It's not perfect, but kind of gets the idea across. Then we have to treat each receipt as a document and the station as its category. Well, that implies we already know which station it came from. So obviously we need some trained data, and that is the receipts that we have used Mechanical Turk or human operators on. We use those as the training data for the system. Next step is we convert each of these receipts to feature vectors. All right, so to convert to feature vectors, we need to tokenize. And if we use the default tokenizer in Scikit-Learn, here are the tokens we extracted. This is potentially useful, but there's all these numbers here. They're kind of meaningless. I don't care if you bought 40 gallons or spent $50. It's not going to help me know which station it came from. So what we actually did is we wrote our own regular expression to try to keep some of these numbers together. So rather than extracting 2 and 569 as separate tokens, if we use this regular expression and keep the symbols together, we extract the entire date and the entire time and these dollar symbols all together. What that lets us do is we can do a filtering afterwards to filter out these irrelevant tokens. We can take out all these prices, this date, this credit card number, and we're left with some tokens that actually look like they might be relevant to this site. So afterwards, once we've tokenized all of our receipts and we've trained it up, I trained my classifier, and then I was interested to see, okay, it seems to be doing something. It's predicting all my test data pretty well, but how is it working? So I wrote this method here, which takes in a trained vectorizer and classifier, and for the category you give it, it will actually show you, here are the top features that I've learned to associate with this category. And again, for this example of the Circle K receipt right here, here are the top 20 features that our classifier associates with this category. So when I trained on several hundred sites, or maybe it was about thousands, I don't remember at this point, there were 26,000 unique tokens that it saw across all of those receipts. And of those 26,000 tokens, here are the 20 that it learned to associate with this site. So the top one is the zip code from this address, which seems like a pretty good way to tell if it's actually that site. Then we see it decided 446, that's the street number. We have Lakeview, and we have Lakeview with a 1. And that's actually kind of cool, because if we had a human sit here and try to write down, how do I determine which receipts are from this Circle K, they might think to type Lakeview, but they wouldn't think to include this error here. But if our OCR is consistently making this error, then this is a good way to identify the site. So the good thing about machine learning is it's actually being trained on the real data that it will be using to predict on that same OCR output with those same mistakes. Down here, there's some merchant number, this 2419, which I'm guessing is the site ID, and even the phone number. So out of all this information, this FRN loyalty, this member rewards, it ignored all of that, and it really did extract the things that you would think are common across all these receipts and identifying to that site. Here's one of those receipts that didn't have an address at all. What did it extract for here? Well, there's not that much information on here, but the number one token it associated with this site is this BP site ID. And if you do notice, our OCR actually does not distinguish between O's and zeros, because it's pretty hard to tell, and you can usually tell based on context. If it's within numbers, we'll just convert this to a 0. But that doesn't matter, machine learning doesn't care. It's like, this is the token that I associate with this site. Cool, so we did all this, we applied it, and what's the last step? This was a before and after. So originally, we were sending 100% of our receipts to Mechanical Turk and paying to have someone look at them, determine what site they're from. After the first time we trained this up and put it in production, we were down to 24% the next day of receipts being sent to Mechanical Turk. So we're saving that 75% of receipts being sent. Last note on what Scikit-Learn isn't. So it does supervised and unsupervised learning, but it's not a deep learning library. If you're interested in deep learning, check out TensorFlow or PyTorch. It's not a structured prediction library, and it's also not a full-featured NLP library, so you might want to use the natural language toolkit for that, which will do things like stemming words. If you have run and running, those have the same stem word, root word, run, and you can associate those together. And NLTK will do that, Scikit-Learn doesn't. I didn't use a natural language processing library for this receipt problem because it's not natural text, not natural language text, so it wasn't necessary. I just wanted the exact tokens as they occur on the receipt. And here's a few more fun links for things to look into, where to get some data to play with, and some other libraries. And last, we are hiring. So if you're interested, please talk to me or email Laura, who's our recruiter, or email me directly if you have questions. Thank you. Yes.
So once you have a classifier defined, you have additional training data you want to apply to it. Does it add it onto it using that same method? Or does
Yes. Scikit-Learn actually, from what I remember, there are ways to. Oh, yeah, sorry. So the question was, if you train a classifier and you have additional data and you want to train that same classifier on additional data, can you do that? And I don't remember off the top of my head what the methods are, but if you Google, Scikit-Learn does have methods to basically add training data to an already trained classifier. Yep.
How do you know which classifier to use for your data?
I would say Google the algorithms. It will, like, if you read the Scikit-Learn docs, it'll tell you like these are particularly good for these types of problems. And if you learn enough about the algorithms, you'll know which ones to use. Also, you can just play with it. It's very easy to swap out. You just call the fit method. So you can try each one and test it and see how it's performing. Yep.
When you've put it to production, have you had to worry about optimizing for performance or runtime?
The Scikit-Learn is actually pretty fast, and I haven't had, I guess, so it depends on how big your model is. So this is all running in AWS Lambda, which has a memory limit and a time limit. And the time for predicting isn't an issue, but it actually takes a while to load the model. And I think the loading of the model, it takes actually a few minutes. But once it's loaded, it's very, very fast to predict. And so you only have to do that loading once. But I think the bulk of the time spent loading is actually just like reading it out from S3 because it's a very big file. And then it does use some memory because it has that whole thing in memory. And it depends on like how many categories and how big the model is. But overall, for this particular problem, I found that Scikit-Learn was actually faster than I expected it would be. Yep.
The example which you used had similar words like cat, dog. So what will happen when we have totally non-similar words in 3 or 4 sentences? So how can this model be ramped up to encounter that case?
I'm not sure I understand the question. Do you mean similar semantically, like cats and dogs are similar, or do you mean?
The cats, away, dogs, like they were repeating words in the sentences.
Yes.
So what if there are no repeating
No
words?
repeating words. If you had no repeating words, then basically, if you picture, you have your columns, you have your features, and your documents, there would be each of your columns, you'd only have a number in one single row, right? There would only be one document with it. And so like in n-dimensional space, like your documents would be completely separate. They wouldn't share any of those dimensions. And you could still use it, and I'm sure it would perform actually very well because it would know like this particular word is with this category, but I don't know, that'd be a very interesting problem. I've never seen like a document that literally shares no words. Yep.
When is the use of the stop words effective?
So the stop words are, the stop words get set when you set your min or max df, because those are the words that were not extracted. Or I can't remember if you can set them manually, but basically stop words are, these are words that by my token rule might be extracted, but I want to explicitly exclude these words and just not include them as features because I know they're not interesting. Any other questions?
Did you go over applications of deep learning when that would be necessary?
I'm not an expert in machine learning. I think it really depends on the problem. We do use deep learning. We have a TensorFlow model for our OCR system. So I'd say for like many more complicated problems, you would want deep learning. Although, I mean, surprisingly for like just these very simple, like naive Bayes, if you actually read about it, it's a very simple algorithm just based on Bayes' theorem. And it performs surprisingly well on many problems. So I think deep learning for very complicated problems, but try these simpler ones first and see if maybe it's enough for your use case. Yep.
What do you do if you're missing data, like in the receipts or something?
In that case, we just send it to manual review, and if we can't extract it, the user just gets an email saying, like, sorry, we couldn't give you cash back.
I had a follow-up question.
Yep.
That's okay. So the OCR, you mentioned that you use
Yep.
deep learning. My question was, how did you build it? Was it using something like PyTesseract or maybe OpenCV? And then since you're using deep learning, is it TensorFlow or PyTorch?
It's TensorFlow, and it's running in Docker and like just a Flask service. I didn't train it. We actually had contractors do it, but the way they trained it was kind of cool because they looked at a bunch of receipts, looked at the fonts that appeared there, and then obviously for any type of machine learning, you need the training data, and in this case, you needed the output. So you need to know what the text is. We couldn't just feed it our receipts that we hadn't transcribed, and we don't transcribe every character. So they looked at the fonts, and then they manually generated training data. So they just generated random strings like A, B, C, D, E, F, G, and then they knew what the output was going to be. They generated the images using those fonts, and that's what they trained it on. And it's a TensorFlow model. Any other questions?
Yeah.
Yep.
Hi, any experience with Weka in machine learning?
I haven't used it.
Okay.
Yep.
Do you use lambdas to deploy other kinds of machine learning models?
The question was, I keep forgetting to repeat it, was have we used Lambda to deploy other models? And no, we haven't yet. Question?
What was the size of the original training data? How many?
So the question was, what was the size of the original training data? And I just don't remember off the top of my head. I think it was the most recent time that I retrained it, because obviously we're always adding more merchants, more sites. And so we're retraining it. We actually ended up limiting, rather than using all of the receipts we have, I think we only used 10 or 20 receipts per site to make the final model smaller. It's still equivalent. And I think it was like a few thousand sites with like 20 receipts per site on that order. Question? Okay, first, I think you raised your hand first.
Yes. The example which you showed actually used the algorithm, like the algorithm was already built in. We were using the inbuilt functions. So what if we encounter a very complex problem in which we have to write our own algorithms? So how we upskill ourselves so that we can write our own algorithm in any case?
So the question was, how can we write our own machine learning algorithms? And again, like I said, I'm not an expert in machine learning. I would do all the reading and see what is out there first. Try out the existing models, because they might be surprisingly better than you think. And the Scikit-Learn library has been very thoroughly tested, and it's an implementation of these algorithms. You can find, like, you could write your own naive Bayes implementation, but why when someone else has spent so much time and tested it so thoroughly? And I'm sure there's people out there developing new algorithms all the time, but I wouldn't know how to do that. Question?
Are you pulling any geo information from when people take pictures?
Are we pulling any geo information when they take pictures? We do have the location data. If we don't save geolocation all the time, but if you're at the site when you're uploading your receipt, we'll just save a Boolean saying you were at the site. And so that is yet another input that we have to tell if you actually are. And we see, like, if you were at that site and the transaction time on the receipt is within a couple minutes, then it's probably from that site.
How often would you say that people are trying to cheat? You know, like you mentioned.
How often are people trying to cheat?
Go
So
from BP to Exxon, right?
yeah,
Or
so I
vice
mean,
versa?
I would say that going from BP to Exxon isn't usually the way people try to cheat. People are, there's many different ways to commit fraud, as we've learned. We have literally had people like type up receipts, print them out, and take pictures of that. So we're always working on like fraud detection and trying to find new ways of finding it. And yeah, I can't tell you the exact numbers because I'm sure there's fraud that we haven't detected yet. So people are creative when it comes to money.
I don't even know if you can tell me this, but how does your company actually make money off of getting refunds?
How do we make money off it? So this is something I can tell you because it's actually pretty interesting. So the way our company works is we work directly with our merchants. We actually get their transaction history from their credit card processor. And for every user, we baseline them as their purchase history at that site prior to using the app. And then after they start using the app, we compare their current. We do a test versus control, so we find other similar users. And we see, are you purchasing more? Or if you've never been to the site before, you're coming here at all. And we can prove to the merchant that the purchase that was made through the app is incremental. And this person, prior to using the app, has never been to your site or only came once a month. And now they're coming 3 times a month. Therefore, you have 2 incremental purchases per month. So we're proving that our app is what's driving the person there. So the way we make money is the merchant is making some amount of incremental profit. We're giving a little bit of that to the user as cash back, and we're taking a bit of as a fee for ourselves. And then the merchant has incremental profit left over. Yep.
This is a broader business use case question, but his question just made me think of it. So has your platform actually incentivized the businesses that contract with you to create GetUpside exclusive coupons, which might help you guys continue making more money?
So the question was, have we created GetUpside exclusive coupons? And we have not yet done that. Yeah. Did you have a question?
Do you ever get receipts directly from the vendors to train on?
Do we get receipts directly from the vendors to train on? No, we don't. We just rely on user-submitted receipts.
I had a question which was similar to a previous question.
Yep.
Was in terms of the size of the model when it's serialized, like with JobLib. So how big is it in terms of the size?
So I think ours was maybe on the order of 1 or 2 gigs. I forget.
1 or 2 gigs.
R1 for this particular problem, and I think that was zipped up. Yeah, I don't remember exactly, but it's on that order. It was definitely not a few megabytes, and it wasn't like tens of gigabytes. Yep.
I have a question about when you mentioned you're saving the model to basically to disk, to a text file or binary file. Is it possible, or would it be helpful to save it to a database or other?
So the question was, can you save a model to a database? And I think probably. I don't see why not, depending on how you want to save it. We're just writing it to a file and then saving that to S3 because that's what works for us. But I think whatever way you want to store it, I don't know if that would help or hurt in any way.
Do you know what the total time span was to train and then validate your model?
Do you mean the runtime or the time it took to write the code?
Runtime.
So the runtime, I think the training was less than 5 minutes. It's pretty quick. I mean, depending on how much data you feed it. If you try to give it too many documents, it won't work. And Jess actually helped retrain it the last time, and it runs within a few minutes, the training.
And validating and verifying and doing.
Yeah, I mean, the test is very fast, the test phase. Do you remember more specifically?
I was having computer issues.
Yeah, yeah. It's usually 5 to 10 minutes on the ones that we were training, I think.
Was that a naive Bayes classifier?
That we used for this problem. I think originally I wrote it as naive Bayes, and then I think the last time we actually saw that logistic regression seemed to perform better, so we switched it to that. But they were pretty close, so that's what we used. Any other questions? Cool. Thank you, everyone.
Joanna, I don't know if you asked the audience, but how many active users in here that have downloaded GetUpside before?
Yeah, I should have asked that. That's a good question.
I've got several friends that
Does anyone
have
use
downloaded
GetUpside?
I will now.
Great.
Now's your chance.
Good. And remember, Joanna 726.